Okay, so in this video, we're going to be talking about the relationship between the dimensions of the row space, the column space, the null space, the domain, the codomain, and the range of a linear transformation in matrix form. So what we know to start with is that matrix A has dimensions m by n. So that means m rows and n columns, just to recall what our matrix organization scheme is here. Now, the first thing to keep in mind is the size of the space that a matrix starts in is called the domain. So the vectors that can multiply the matrix. So in this case, the domain is going to be Rn, and the codomain is the size of the space that the vectors end up in after multiplying by the matrix. So in this case, the codomain is Rm. Now, how does the codomain differ from the range? The range are the set of vectors in Rm that the matrix can actually project onto. So the range is a subspace of Rm. Now, it may be all of Rm, but it might not be. So that's the distinction here. So the codomain is going to be determined strictly by the size of the vectors that you create when you multiply a vector by the matrix. Whatever size vector you get out, that's the codomain that you're in. But if you can't get to every vector in the codomain, then the range is going to be a subspace of Rm. If you can get to every vector in the space, if it's onto, for instance, then you're going to have the range and the codomain be the same. But the range and the codomain do not have to be the same. You can have a projection, a transformation, which is not onto, so that it can't get to every possible vector in the space, so that there are inconsistent solutions. Okay, so that's the sort of basic stuff. Now, these, the domain and the codomain depend only on the size of A, the size of the matrix. Now, the range is going to be indirectly connected to the column space, because the column space is what's going to be the range itself. So, because those are the basis of the columns are the vectors that you can project onto. So any vector which is a linear combination of the vectors of the column space is in the range. So the column space is the set of vectors that are linear combinations of the vectors in the column space, and that is equal to the range. So the dimension of the column space and the dimension of the range is going to be the same. equal to the rank, which is the number of pivots. Now, so far we haven't said anything about pivots because that hasn't been provided to us, but that is now another component. So let's say the number of pivots for our matrix K. So if the number of pivots is K, the dimensions of the column space is K, the rank is K, the dimension of the range is K, and the dimension of the row space is K. The null space is not K. The dimension of the null space is the number of columns minus the number of pivots. So n minus K. Now let's look at a specific example, and then we'll look at, again, just calculating these from a generic perspective. All right, so suppose that we have a matrix A, and I used this in a previous video. So this is our 3x5 matrix, and when I row reduce it, I get the following. So what do we know? So we know that M is 3, N is 5, and K is 3. So we can say that the domain is R5. Because in order to multiply any vector by this matrix, by definition of matrix multiplication, you have to have a 5-dimensional vector. We also know that the null space is a subspace of R5, of Rn generally. So the vectors will have to be 5 components long, but we have some pivots, so the dimension of the null space won't be 5. The dimension of null A is actually just going to be 2 because there were 5 columns, we have 3 pivots, and therefore there are 2, and you can see this from the reduced form of the matrix, there are 2 free variables left, and that's what gets us our basis for our null space. So the domain is R5, the null space is 2-dimensional subspace of R5. The codomain is R3. The range is also here R3, since the rank, the number of pivots, is 3. The dimension of column A is 3, and that is also equal to the dimension of row A. The rank, the dimension of column A, the dimension of row A, they're all the same, and it all depends on the number of pivots. And as I said, the codomain and the range may be equal or they may not be equal. So again, let's consider a slightly more generic example where we're just thinking about the dimensionality and not the individual matrix. So suppose you have a 7x9 matrix with 5 pivots. what is the dimension of the domain? What is the dimension of the codomain? What is the dimension of the column space? What is the dimension of the null space? What is the dimension of the row space? And what is the rank? And then finally, what is the dimension of the range? So these are all sort of standard questions that you can ask. Obviously, some of them are going to be the same and some of them are not going to be the same. What is the dimension of the domain? Well, the domain, again, depends on n. And so it's going to be 9 because the domain is R9. You need to have a 9-dimensional vector in order to multiply by a 7x9 matrix. So the dimension of the domain is 9. What is the dimension of the codomain? The codomain is the size vectors that come out of matrix multiplication. So that is M. So that's going to be 7 in this case. What is the dimension of null A? That is going to be the number of pivots, which is going to be 5. What is the dimension of null A? In this case, it's going to be 9 minus 5, which is 4, because it's n minus k. What is the dimension of row A? Well, it's going to be 5 in this case, because it's the number of pivots. What is the rank? Just another fancy way of saying what is the dimension of the column space or the row space. What is the dimension of the range? Same deal. It just depends on the number of pivots. So this is a nice question that I like to ask on an exam for my students. Given a matrix of a particular size with a certain number of pivots, tell me about the dimensions of these various subspaces associated with matrix A.